All right, so 10.2, that's 10.2 right there. I made a little mistake when I typed this out, is kind of like part 2 of what we dealt with in 10.1. We're still looking at non-right triangles. In 10.1, the focus was on the law of sines, using that to solve non-right triangles. Here we're using another tool called the law of cosines. So the issue with the law of sines is there's a couple of cases of non-right triangles that the law of sines won't be able to solve. In particular, those are the SAS cases, side, angle, side, and SSS, or side, side, side. The law of sines does not work in either of those cases, at least in the first step. So the law of cosines is the tool that we use in those cases. Now what I'm doing here is I'm deriving the law of cosines, but then we're going to look at a couple of examples where we use it to solve some triangles. So once again, we're dealing with a non-right triangle, and I've arranged this triangle so that my base is C. And that's kind of an arbitrary choice. I can choose A or B to be my base, but I'm going to use C here. And then notice, like in 10.1, we drop this perpendicular right here to create the height or the altitude of this triangle. But that does something else. It also splits the base into two parts, not equal parts, not necessarily. So I'm going to call one of these parts X. That would make the other part C minus X if the whole base is to add up to C. So what I'm going to do is use the fact that creating H here actually creates two different right triangles within this larger triangle, and use some tools that I know that apply to right triangles. So for one thing, alpha, this angle right here, I know that cosine of alpha would be adjacent over hypotenuse, or x over b. If I arrange that, I can solve for x. It comes out to b cosine of alpha. That's going to be used in a moment, but we're just going to set it aside for now. If I take the exact same right triangle and then look at the Pythagorean theorem for that right triangle, the sum of the squares of the legs should equal the square of the hypotenuse. X squared plus h squared equals b squared, which I have written right here. Again, this is something I'm going to use in a moment, but I'm just setting it aside. So two little relationships between some values in this triangle. Okay, going down a little bit further, what you're seeing on this line right here is another application of the Pythagorean theorem, but to this right triangle. So if I use the Pythagorean theorem, I want c minus x quantity squared plus h squared equals my hypotenuse a squared. That's what you're seeing here. Then if I were to take this expression, c minus x squared, and expand it out, I get c squared minus 2cx plus x squared. Now the reason you're seeing parentheses right here, I put these parentheses in after I expanded that out. Notice we still have the plus h squared showing up here, a squared and a squared. I grouped these two up, the x squared and the h squared, because those show up here, x squared plus h squared. We know that this is equal to b squared. So this is going to give me a b squared when I make that substitution. Okay. Additionally, the minus 2cx that I have in this term, I'm going to replace that x with this expression up here, since x is equal to that. If I did that and rearranged the factors a little bit, I get minus 2bc cosine of alpha. Finally, this thing right here is the law of cosines, or one of the three versions that we're going to talk about for the law of cosines. But you typically don't see it written with this arrangement of terms, so I rearranged some things. I put the a squared on the left side, this expression on the right side, and I put the b squared and the c squared first on the right-hand side. So just after some rearranging, this is what the law of cosines typically looks like, the way that we write it. So moving down here, this is straight out of your book. This is the way that they write out the law of cosines. And in this case, you're seeing the first line here corresponding to what we showed up here. It says a squared equals b squared plus c squared minus 2bc cosine of alpha. These other two versions of the law of cosines are simply what you get if you go through that same derivation that we just went through, but if you were to make either a or b the base of that triangle instead of c, like we did. you don't need to think of these as three completely different formulas that you need to memorize. You should notice that they look very, very similar. And the trick, if you can remember one of them, you can basically say that you know the other two by remembering this little pattern. So A, in this first equation here, the angle that's opposite A is alpha, and that's the only angle that shows up in this entire formula, if you will. So the side that's over here by itself, a squared or b squared or c squared or whatever, is going to tell you which angle shows up in the cosine here. B goes with beta, C goes with gamma. Similarly, if there's an a squared on the left-hand side here, you won't see any more a's in this expression. You'll only see the other two sides, b's and c's. Notice I have b squared plus c squared minus 2bc. So for example, if I needed to use this version of the law of cosines, if I see a c here, then I'm expecting only a's and b's here. Okay? So little things like that help you remember this stuff. These expressions down here, these are just rearrangements of the terms in any one of these three expressions. In particular, if you were to take any one of these, I said expressions, I should have said equations. If you were to take any of these equations and solve for cosine of whatever angle you have, you get one of these three. You do not need to memorize these. You just need to know these, because you can always get these by solving this. So let's take a look at a couple of examples where we want to evaluate, we want to solve a triangle. Now, I've already worked out these examples in advance. So here we're given what's called an SAS case. So I have two sides, B and C, and the included angle between them. Law of cosines will help us with this. So the law of cosines looks like this. A squared equals b squared plus c squared minus 2bc cosine of 30 degrees. 30 degrees being my alpha in this case. I'm going to plug in the b and the c as well down here. And a squared is equal to this big expression. Here's the important thing that some people will occasionally forget. This is a squared, not a. So if you want a, you then have to take the square root of all that. Notice, as I usually do, I haven't worked anything out until the very last step, because when you put it all in a calculator, you want to reduce rounding error. Not a huge issue for this one, really, because you're working with a lot of integers. So you could have evaluated 12 squared and 24 squared ahead of time, but if you were to plug all this into a calculator, A is going to come out to approximately 14.87. So here's the thing. Whether you're dealing with the SAS case or the SSS case, you're going to need the law of cosines, but you only need to use it once. Because once you've done that, notice I've gotten one of the other sides, the only side that I didn't have for this triangle. I now have enough information to start using the law of sines to get the remaining missing measurements for this triangle. So if I set up my law of sines, I want to use what I just found. Sine of alpha over A. That would be sine of 30 degrees over 14.87, which we just got. Equals sine of beta, we don't know beta, over B. We do know B. B is 12. So this lets me set up the law of sines, which I would then use to solve for beta. Notice I cross-multiplied here to get this expression. Solving for beta means taking the inverse sine of both sides of this, which I did here. The inverse sine, once you plug it into a calculator, is approximately 23.8. I didn't need the law of cosines for that second step. I just needed the law of sines with what I already found. Finally, if you know alpha and you know beta, you have enough information to get gamma. Subtract those two angles from 180 degrees. Gamma comes out to 126.2. And again, it's always a good idea to make sure that your answer is reasonable by looking by arranging the angles that you found in order from smallest to biggest, and make sure that those opposite sides, those corresponding sides, have the same order. So you notice A, B, and C. A is 14.87, B is 12, C is 24. So these sides, in order from smallest to biggest, are B, A, and then C. That means my angles, in order from smallest to biggest, should be beta, alpha, gamma. Well, is that what we got? Beta was 23.8 degrees. Alpha was 30 degrees, gamma 126.2. That's the correct order. So again, that doesn't mean that you have a correct answer, because we can still have the same arrangement from smallest to biggest, but with slightly different numbers. It just is a way of sort of, ruling out that you made a huge mistake. Let's go ahead and scroll down and try one more example. This is an SSS case. So in the case of an SSS triangle, you have all three sides given to you. That means the goal here is to find the angles, the missing angles. So we need the law of cosines for this. I'm going to start by finding the angle alpha. Cosine of alpha is what I want to have show up in my law of cosines so that I can solve for that. So plugging in the things that we do know, a, b, and c, I have a squared equals b squared plus c squared minus 2bc cosine of alpha. Plugged everything in. And again, if I want to solve for cosine of alpha, I want to isolate it. This expression here is a version of what we are using here. And actually, this should be a negative down here. Okay, but once I get down to this, cosine of alpha equals this number, whatever this comes out to be, I solve for alpha by taking an inverse cosine. And yeah, you can plug this into a calculator at this stage if you want to. I'm choosing to wait until the very last step. But what I get is approximately 27.66 degrees once I get here. Now, like we said before, we're not going to need the law of cosines again, because knowing this is enough to start using the law of sines for the remainder of this problem. Using this 26.66 degrees, I'm going to do sine of alpha, which is what we just found, over a, 5, equals sine of beta over b, 7. We know b. So again, you would cross multiply and then solve for beta by taking an inverse sine. Beta will come out to the inverse sine of this, which is equal to, well, approximately 40.54 degrees. Okay? Once you have those two angles, the third angle is the easy part. You just subtract the other two from 180. In this case, we get that gamma is approximately 111.8 degrees. Okay? So that's a couple of examples of solving triangles. In the next video, we'll look at a couple more applications of the law of cosines. One is that it technically gives us something called Heron's formula or Heron's formula. It's another way of calculating the area of a triangle if all you know are its three sides. And then we're also going to take a look at how the law of cosines is useful for finding distances. But we'll save that for the next video.